Hello, everybody. Let's start our seminar today. The first talk is by Nguyen from Hanoi, and Bath Center for Mathematics is going to talk about cohomology of contact loci. So,
thank you, Professor Phung Ho Hai, for the. Today, I am going to talk about the cohomology of contact loci. This is based on the work joined with Javier Bobadilla, Nero Boudou, and Quý Thường Lê. This talk will appear in the Journal of Differential Geometry. So let me start with the outline of the content of the talk. The first part is our motivation. The second part, I'm going to talk about the Maclin spectral sequence concerning Fleur cohomology. The third part is about our spectral sequence. And the last part is the summary of the talk. So let me start with our motivation. We studied the polynomial f over the complex field with isolated singularity at the origin. And by the Minor theorem, we have the following Minor fibration, which delta and epsilon is small enough. Here you can see that the restriction of f to the bond b epsilon is perfect with the invert of f of d delta star, and this is called Minor fibration. And the fiber of this fibration is called Minor fiber. As we know, any leaf of a loop around the origin in C induce an diffeomorphism 5 on the Minor fiber M, and this is called monoromy map. This map gives rise an action of phi on the cohomology group Hi of M on the with coefficient that, and this is called monoromy. The Minor fibration is an important problem in singularity theory. And now it's for its natural number m, we define the mth left-hand number of f at the origin is defined by the equation. I mean, lambda of phi of m is the alternative sum of the trace of phi m. And here it's the m contact locus of f. It's defined to be the set of own arc in the arc space of the m arc space of Cn, such that f of phi is equal to t power 2m, and phi 0 is 0. I will define more clearly the m contact locus of f later. This is only for the motivation. And in 2002, the Knapp and Loci proved that the Euler characteristic of the m contact locus of f equal to the left-hand number of phi m. And recently, Maclin observed that the Euler characteristic of Fleur cohomology of phi m is equal to the left-hand number of phi m. And from these observations, Zayden asked a question to the Knapp and Loci that, and how similar are the cohomology of with compact support of the contact locus and the Floer cohomology of phi m of the monoromy, of m iterated monoromy. Here I recall something about the Floer cohomology. And as we know, Floer cohomology is an essential technique in symplectic topology and low dimensional topology. And it has made possible the resolution of many difficult problems like unknown conjecture and continue to do so. As far as I know, the Floer constructed its cohomology in order to prove the unknown conjecture. And let M and omega be a compact symplectic manifold, and phi is a symplectomorphism. Floer cohomology of phi, denoted by 8f of phi, is considered as a mock cohomology of an actional function A on the space of tweet loop. This is infinite dimensional space. And the tweet loop is the space of omega phi such that the set of all omega gamma from R to M such that phi of gamma t plus 1 is equal to gamma t. And the Floer chain complex is generated by the fixed point of phi and graded by the Connolly-Sandy index. This is the short overview of Floer cohomology. I will come back to the question of Dryden. And recently, Maclean constructed a spectral sequence converging to Floer cohomology of M iterated monoromy phi m. And he also asked a question if there any similar spectral sequence converging to the cohomology with compact support of M contact locus of F. And this is the main motivation of our work. And let me first introduce a spectral sequence of Maclean. And for that, we need some notation about resolution of singularity. By a log resolution of X of the zero locus of F, we mean a proper morphism 8 from Y to X, such that the restriction of 8 to the over the complement of the zero locus of F is an isomorphism, and such that the pyramid of the zero of the morphism is a divisor with normal crossing. And we denote by EI. I in A is the set of irreducible components of the divisor of F of this map, and defines a multiplicity of F along EI by equality of divisor, by the equality of divisor in the equality. Here it's Ni is the multiplicity of F along divisor, irreducible divisor EI. And here we need some more notation, and I mean technical notation about M separating resolution of singularity. A log resolution 8 is called an M separating resolution if for any two divisor which intersect EI and EJ is non-empty, then the sum of respective the sum of corresponding multiplicity must be bigger than M. This means M appear in the name of M separating resolution. And by Matlin, we know that M separating resolution always exists, and it can be obtained by finite blowing up. Here is some more notation on the resolution of singularity. We consider again just M separating resolution, and with the divisor define as before. Now we define the EI not. It's that EI remove on the other point in remove on the point in other irreducible divisor, and EI not tinder the cyclic cover of degree Ni, and it is defined by the following formula. This is defined locally in any neighborhood, in some neighborhood U, a point in EI naught. It's defined by the set of Z and Y such that Z power 2 Ni is equal to U Y invert of U1. And here it's that Y is that the local coordinate of the point in U, and Yi is the coordinate defining locally the divisor EI. This cover was considered by Acampo. First, I think firstly by Acampo, and then by the algebraic definition is by Deneb and Loci. And some more invariant of resolution of singularity. This first one is discrepancy, denoted by nu I minus 1. Of EI is defined by the equality of divisor. Here, the ky over x is the relative canonical divisor defined by vanishing of the determinant of the differential of 8 of the resolution. Now we consider only the exceptional divisor. By exceptional divisor, we mean the divisor that it's emitted by it. It's only the origin in Cn. Now, we denote by Hm the set of I in adject. I mean, adject is the set of all exceptional divisor such that Ni divides M. And by this, we can define the Ki is the M over Ni, and this is an integer number. Now to construct Matlin spectral sequence, we need to fix first some M-po divisor with special M-po divisor. We mean that the omega I be a positive integer so that the divisor defined by the minus of omega I EI is M-po. This only exists by the resolution of singularity by blowing up. And here it's for we define one more set. It's just at MP. It's the set of I in SM such that Ki omega I equal to minus P. I will show you the Ki. Let remember that Ki is the M over Ni. That means Ki times Ni is M, and omega I come from ample divisor. And here is Maclean's spectral sequence. He proved that there is a cohomological spectral sequence converging to the Floer cohomology of M iterated monotomy, which the third bit is it. The third bit is completely computed by the homology of the cyclic circle cover of EI node. And this cohomology was also considered by Acampo in his famous paper. Now, I am coming back to art spaces and contact loci. Now I will define in detail on the notion I mentioned before. And here's let X be a smooth complex algebraic variety, and F from X to C be a regular function like polynomial. And the mz space of X is the space we denote by Lm of X of on arc modulo T power m plus 1. And we can see that the C-rational point of the mz space of X is a morphism from the spectrum of Ct over T modulo T m plus 1 to X. And the arc space of X is the projective limit of this space, of the mz space, and it denotes like it. And we can consider the C-rational point of the arc space. It's a morphism from spectrum of C, formal power series, one variable formal power series over C, 2x. And now we can define what is M contact locus of F. It is the set of on Z. Here we can go also arc phi in the Z mz space of X, such that the f of phi is to T power to M, and phi 0 is 0. This is the main object we study in this work. And this is the first remark about the mz space. The first that space of X is the tangent bundle of Tx of X. This is clear from the definition. Now we can consider some simple example about the mz space and the M contact locus. Here we consider very simple example, like X is C, that's the affine, the complex affine, and Fx is X squared. And the mz of X is a set. We can give coordinates on element of the mz of X like this. The set of arc of form A0 plus A1t plus AMT power 2m. And here is AI is in C. And from it we can see that the mz of X is the C power to m plus 1. And similarly, we can see that arc space of arc is a set of four arcs or with the coefficient in C. And the M contact locus of F is empty if M is odd, because we here you can see here the power of Fi is power 2, I mean I square, and then if M is odd, then we have did this I did this 2 times, and in case that M is even, then the M contact locus of F is the set of arc from A0 plus so on to AM power to M, T power to M, which I equal to 0 for all I smaller than half of M, T half, and which A M over 2 is must be 1 or minus 1, because we see that A M over 2 square is 1, because 1 is come from the coefficient in the definition of F. And then we can see easily that the M contact locus of F is isomorphic to C M power M over 2, and this join with C power M over 2, and then it's 2 copy of C power M over 2. And here's some more example. It's non-trivial example. And in this case, I is C square, and here the complex surface. It should be here should be surface, and F is the X square minus YQ. And by the same argument as before, we can see that the M that space of X is isomorphic to C power to 2 times M plus 1. And we can also compute the X, 1 of F and X, I mean the first and the second contact locus of F, like that. Here are 2 remarks about the contact loci. The class of the contact locus, the M contact locus of F in the Gaussian ring of variety are coefficient of the motivic zeta function of F. In fact, the motivic zeta function of F is defined as the sum series, and as we know that the limit of this series is the minor of the motivic mean fiber. An object was studied a lot recently. And the second remark is about the dimension of contact loci. Mutstata in 2002 gave us several relations between the dimension of contact loci and log canonical threshold of F. This means if we know the dimension of contact loci, then we can compute the log canonical threshold of F. This invariant is a very important invariant in not only in singularity but also in complex geometry. Here we come back to the question of Zayden, the Neplose, and Macklin. And here we see that by Macklin, we have a cohomological spectral sequence converging to the Floer cohomology of the M-iterated monorome with the third bit. And inspired by the question of Zayden, Macklin asked the following question: is there any similar spectral sequence for the cohomology with compact support of the M contact locus of F? And did it our main motivation for this work? And we answer yes in the talk. Here is our spectral sequence, and I recall that the omega I are positive, and the divisor is ample. And as MLP I defined before, but here is the recon to show you about our spectral sequence. Here's our main result. There is a cohomological spectral sequence converging to the cohomology with compact support of the M contact locus of F with the first bit E1PQ. It's the direct sum of the cohomology. No, it is homology of the. It is cyclic cover of EI naught. All the homology come from resolution of singularities. EI naught on these things are come from. That means we can compute, in some sense, the cohomology with compact support of the M contact locus of F via the invariant in resolution of singularities. And here's something about the degeneration of our spectral sequence. From our spectral sequence, after tensoring with rational field, only the first deep page of the spectral sequence can be contained non-zero differential. That means our spectral sequence degenerate in at least in the D plus one page, and this is different from our spectral sequence and Macklin spectral sequence. Macklin cannot say anything about the degeneration of his spectral sequence, and here to prove that we need the proof of the proposition is not so difficult. It comes from the construction of our spectral sequence and the mixed structure. I mean, our spectral sequence admit is a mixed structure spectral sequence, and then we can get this proposition from some property of mixed structure. Here is an example computing our spectral sequence in a very simple case. If F is equal to R, it's just that a polynomial in one variable, and then the identity map is an M-splitting resolution. Then we can compute the third bit of our spectral sequence like it. It is a simple calculation. And then from our spectral sequence, you can see that the here should be the cohomology with compact support of I'm sorry, the sigma here should be 0 because in our paper actually we study more in general case. And I mean, from the spectral sequence and the calculation, we can compute the cohomology with compact support of the M contact locus of F. And did also compatible with the isomorphism compute directly from the formula of the M contact locus of F. I mean, this formula it's compute easily directly from the definition, but these are computations that show that they are compatible. Now I'm going to the construction of our spectral sequence, and for that we need some technique. This is the technical notation. Like this is nature projection from the aspect of X to the mz of X, and this is from the Lz of X to the mz of X. This is nature morphism and truncation. And now we denote by xm this is the M contact locus of F, and xm in infinity it's pre-image of the M contact locus of F in the aspect, and similarly the xml is the pre-image of the M contact locus of F in the Lz space of X. And the first result for this notation is the following isomorphism. We have the isomorphism between the cohomology with compact support of the pre-image and the XML, and the cohomology with compact support of the contact locus, the M contact locus. This isomorphism is important because to construct our spectral sequence, we cannot construct it directly in XM. We have to move it to higher depth, and that's why we need it to we need it isomorphism to compute the cohomology with compact support of the M contact locus of F. And this lemma is a version of Thom isomorphism for R5 fiber bundle. Yeah, Thom isomorphism is completely similar, but instead of R5 bundle, he studied vector bundle. And now we will construct a spectral sequence for cohomology with compact support of this variety. It's XML. From now on, we consider only XML. And for this, we need for a spectral sequence, we need only a filtration on that space, and the filtration is constructed as follows. We consider again the M separating resolution of X, and now we define the XMI of infinity. It's the set of own arc in this space, in the arc space of X, such that gamma tilde 0 belong to EI naught. And here, gamma tilde is the lifting of gamma. That means we consider on the arc in this aspect of X such that its center in it is centered in the EI naught. The center of an arc in a resolution means the center of its lifting. This is the gamma tilde 0. It's the center of gamma tilde, and gamma tilde is the lifting of gamma. And then now we just define the XLMI is the image of this set in the LZ space of X. And this is the first important result for all this notation. It's from, and here we need M separating resolution. Why this is very technical, but it's make all the computation easily. From our resolution is M separating, and now by a theorem of I, Lassafan and Mustata, for all L big enough, we have this. We have this identity. This is equality. This is not definition, and this is these two equation equality is not simple. It's not clear. For this we need two things. It is our resolution must be M separating, and the second thing it's something for the third one. It's like it's come from Greenberg theorem, and the second one it's come from the net and loci theorem for the chain variable formula in motivic integration. I that means that these two identity are not simple. Now, for that, now we can define our filtration. The filtration of XML is that just define P of XM. This is filtration. It is the union of only the space, and this is FP. It's the complement of complement from our filtration, and it equal to this. I mean, from these two identity, and we can see this. Here are key lemmas from these three lemmas. We can get our theorem, get our spectral sequence. The third one claims that the set of FPXLM is closed in XLM for any integer. And the second lemma is about the irreducible decomposition of this set. And the third one is about this set, this variety. This variety is smooth, and we know we can compute its dimension, and we show that it has the same homotopy type of EI not Tinder. And here, this is the third lemma. the third lemma say that this set is closed, and this means that we can get spectral sequence. Given any filtration with a closed subset, we can get a spectral sequence. I mean, any filtration induce a spectral sequence conversing to the cohomology with compact support of the variety. And that means we get the spectral sequence with the third bit. This come from a spectral sequence theory. And here I just recall that the notation of F and P in bracket, the union of this set. And now to compute this cohomology, we need to compute the cohomology with compact support of Z, and we can easily get the diagram of corresponding cohomology if we know that all these sets are closed, and this is the second lemma, and all these sets are here. I come back here. All these sets are closed. It's even more that they are irreducible component of this set. And from this, we can get easily this identity. And now it remains to compare the cohomology with compact support of XLMI. I mean, it's for XI. And for this, we apply the third lemma. This is the third lemma. The third lemma saying that this set is smooth. Complex variety smooth is important because we want to apply Poincare duality. And the second part is we can compute the dimension of this variety. And the third part of the lemma is this smooth complex variety has the same homotopy type as I not Tinder. And from this we can we get from the third lemma we can get easily this identity, and then we get it. And it, yeah, the last identity is the formula of computing the third bit of our spectral sequence. I come back to show you. Did it appear in the third bit of our spectral sequence? Yeah, here is the spectral sequence from the filtration, and it is the spectral. This is the formula computing them, and here that means we get our spectral sequence from the 3 key lemma. Now, here is a conjecture we pose in our paper. Yeah. Here it's the first. It's a question by Zeiden, Dudenap, and Lothe. Ask how similar are the cohomology with compact support of the M contact locus of F and the Fleur cohomology of M iterated monodromy. And we can see now from this one is Maclean spectral sequence. This one is Maclean spectral sequence, and this one is our spectral sequence. And we can see that the footbed, the footbed of these spectral sequence are the same after Earthship. I mean, the ship is A here. I denote by AI. They depend only on the dimension. I mean, the number variable of F, the dimension of I. and M. And from McLean's spectral sequence and our spectral sequence, we conjecture that the cohomology with compact support of the M contact locus of F is equal to the Floer cohomology of the M iterated monoromy. I mean, after a sum shift, it's a shift A. And if we can prove the conjecture, we answer completely the question of Zayden. And we prove that the conjecture is true if M, for special M, here M is the multiplicity of F at the singularity, here at the origin. And more generally, we have, if F is the multiplicity of F, of the morphism F at 0 at the origin, and F is the mean of fiber of the tangent cone of F. Here we consider only the mean of fiber of the tangent cone of F, not mean of fiber of F. Then we have the following identities. The cohomology with compact support of the M locus of F equal to the homology of F after sum shift, and this equal to the homology, the Floer cohomology of M iterated monoromy, and this prove the conjecture for the special this special case, in the case that M is the multiplicity of F. And recently, McLean, in a talk in Institute for Advanced Study in Princeton, he claimed that he proved the conjecture in general. Yeah, I am waiting for a proof on AGEA, but it is not available on AGEA now. Here is the summary of my talk. The motivation comes from the McLean spectral sequence converging to the Floer cohomology of the M iterated monoromy, and he asks a question for he asks for a similar spectral sequence for cohomology with compact support of the M contact locus, and we answer his question by constructing our spectral sequence. And it is interesting that the third bit of our spectral sequence and the third bit of McLean's spectral sequence are the same after some shift. Then we conjecture for an isomorphism of to this cohomology. Here is the conjecture, and this later is the conjecture. We prove the conjecture for the K the K when M is the multiplicity of F, and McLean told that he had obtained a proof for the conjecture. And what next? What is the future work in the direction? Come back to the third one is about the degeneration. If we have the conjecture, if we prove the conjecture, then we can see that we can say something about the degeneration of McLean's spectral sequence. This is unknown now. The second thing, it's about, we know that in the left side, in the cohomology with compact support of the M contact locus, because this set its variety, then complex variety, then it admit a mixed hot structure, and then if the conjecture is true, we can see that the Flow cohomology of M iterated monomy admit mixed hot structure. This is also nice for symplectic geometry. And the last one is about something, if you can apply some, because we know that in the theory of flow cohomology, they have a lot of nice property. And if the conjecture is true, we can apply such nice property to the cohomology compact support of the M contact locus. Something like, yeah, we know that the flow cohomology admits quantum product, and if this is true, we can add what is quantum product in this side in the algebraic geometry. So I finished my talk here. Thank you for your attention.
Yes, thank you, Duke. Thank you very much. It's a very nice talk. So we have some time for question or comments. I'd like to ask about the case m equal to 1. Is it still very complicated, or I mean, can you have that?
Usually it's very simple, because it's zero. The M contact locus at zero if M smaller than the multiplicity.
Okay. Yeah.
Empty, I mean.
Yeah.
Excuse me. Hello?
Yeah. Go ahead.
So the difference of the shifting is a constant for M as well?
Sorry, I cannot hear you.
The shifting of the spectral sequence, AI prime mass AI, are they constant as well for OM? Shifting of the spectral sequence I, are they constant as well for OM?
Yeah, I understand your question. It is not. It's depend strongly on M. It is not constant.
And what's the new version? What's the new version of your conjecture?
Maybe you can try to type, because it's hard to hear you.
Jen, can you repeat the question, because I think I can hear you easily than the alien in the room. I am sorry, I cannot hear the second question. Can you type, or because the sound is not.
노트북으로 가져가. 노트북 가져가셔서. 네, 그래도 좀 높여야지 사람들이.
Can you repeat the question? Or someone like Jen, can you? Can you ask the question?
Would you like to say something?
Are you typing a question, or?
いいですか? Now I have some private question.
Okay.
Is the former president Nguyen from the Thang University, is he yet fine? This is a private personal question.
Who?
Because he's my classmate at Tokyo more than 50 years ago. Do you know him personally?
Nguyen, the topologist?
Yes. Topologist, yes. He has stayed in Tokyo as a foreign student.
Yeah. So the question is he is fine? Look, I guess you
He's
know.
fine,
Yeah.
I think he's fine, yeah.
Okay, yeah, good. I met him in Hanoi 10 or 15 years ago. Yes. Thank you.
So, thank you.
Okay, so if there are no more questions, so let's thank Đức. Okay, and so we will resume in 17 minutes. Okay, the second talk will start in 17 minutes, 17.
Okay, thank you.
Okay,
Thank you.